Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on gravitational field from October-November 2021 paper 4 variant 2. I said this question is very important because in this question, we will talk about gravitational field against distance graph. And also we will discuss how this graph is linked with G against distance graph. And if one graph is given to us, how we can sketch the other one. And also what kind of information we can get from potential against distance graph and lot more on gravitational field in this class. For part A, we need to state the relationship between gravitational potential and gravitational field. So let's try to understand how these two they are linked together. We can simply say that G is equal to negative of d phi over dr. That's all what we need to understand, and that's all what we need to write down for the answer of this question. So these two things we have to mention. Now let's try to understand what exactly it is meant by d phi by dr. This is called potential gradient. D phi by dr, simply we can say this is potential gradient. In this case we are talking about gravitational potential, so you can also say gravitational potential gradient. Now let's try to understand what exactly is gravitational potential gradient. In order to understand gravitational potential gradient, we need to understand the relationship between distance from the center of the planet and potential. So this is how these two are linked together. Or simply we can say potential is directly proportional to 1 over r. Now if we sketch a graph between potential and r, let's say we have potential on y-axis. So here we have potential, this is on y-axis, and we have r, the distance from the center of planet. Let's try to sketch graph between potential and distance from center of planet. In order to sketch the graph, we will imagine that there is a planet that is placed at the origin, and the radius of this planet is equal to capital R. Before we sketch this graph, we also need to understand this formula is only true for the potential outside of the planet, and this is not true for potential inside the planet. Means we cannot determine the variation of potential with distance inside the planet using this formula, and this is only true when r is greater than radius of the planet, means outside of the planet. We can only use this formula outside of the planet, so we have to be very clear about this point. Now let's try to sketch the graph between potential and distance from center of planet. If we sketch the graph between potential and distance from center of planet, the shape of the graph will be somewhat like this. Let's try to understand how we can determine value of G if potential against distance graph is given to us. In order to determine value of G, simply we need to find the gradient of this graph, and then we need to take negative of that. So simply we can say G is equal to negative of potential gradient. So let's try to understand this one with one simple example. Let's say we need to find the value of G at this point. So first of all, we need to draw the tangent line at this point. So this is over tangent line, and if we take the gradient of this and then we take negative of gradient, that is equal to G. So this is what we need to understand about G and potential gradient. This is how they're linked together. So simply we can say G is equal to negative of potential gradient. So this is the point you need to understand. G is equal to negative of potential gradient. Means you will take the gradient of potential against distance graph and then you take negative of that. That is G. If you are very curious about what will be the shape of the graph inside the planet, shape will be kind of parabolic inside the planet. But this is not part of your syllabus. You need to understand how to sketch a graph outside, means from the surface of the planet. Now let's try to understand how we can write down the answer for this question. In order to write down answer for this question, you have to mention 2 points. One point is this one. If you have written gravitational potential gradient, you will get 1 mark, means this is M mark. It has to be in your answer. And if you have mentioned about negative, you will get the 2nd mark, and that is A mark, means answer mark. And this is how you can write down a proper answer. As you can see, in this case, I have mentioned gravitational potential gradient. If you have written this one, you will get 1 mark, and if you have also mentioned about negative, you will get second mark. And this question has only 2 marks. For part B, it is given to us a moon of mass capital M and radius r orbits a planet of mass 3m and radius 2r. At a particular time, the distance between the centers is capital D, as shown in figure 2.1. Point P is a point along the line between the centers of the planet and the moon at a variable distance x from the center of the planet. Mean x is the distance from the center of the planet. In figure 2.2, the variation of potential with distance from the surface of the planet to the surface of the moon is given to us. And question is asking us, explain why potential is negative throughout the entire range. X is equal to 2r means x starting from this point to x is equal to d minus r. Means from the surface of this planet to the surface of the moon. Why it is negative. In order to understand this one, we need to understand first point that potential is defined 0 at infinity. So this is the first point we need to understand. At infinity, potential is equal to 0. So simply we can say potential is equal to 0 at infinity. And also at infinity, we take gravitational potential energy also equal to 0. First of all, let's try to understand gravitational potential energy in a very simple way. Imagine that we place a unit mass at the surface of this planet. Let's say the mass of the planet is capital M and unit mass is small m. So this is unit mass. You can imagine that this is 1 kg. Or simply we can say this is unit mass. If we move this unit mass up, in this case, gravitational potential energy of this unit mass, this will increase. And in this case, work done by gravity. So I will say work done by gravity, that is negative. So the work done by gravity is negative. So when work done by gravity is negative, gravitational potential energy increases. And now if we move this unit mass from here to down, in this case, gravitational potential energy of this unit mass will decrease. And in this case, work done by gravity is positive. So very important point you need to understand. When work done by gravity is positive, gravitational potential energy decreases. When work done by gravity is negative, gravitational potential energy increases. Now let's try to understand how we can define potential in a proper way. In order to define potential in a proper way, we will imagine a planet of mass capital M at this point. Then we will take another point at infinity. Imagine that we have a unit mass that is placed at infinity, and this unit mass is at rest. So simply we can say the speed of this unit mass is equal to 0. And we want this unit mass to move to another point, let's say to point P. And the distance of this point P from the center of the planet is equal to r. If we move this unit mass from infinity to point P, at point P, the speed of the unit mass again has to be 0. It simply means that when we move unit mass from infinity to point P, there is no change in kinetic energy. But we need to understand gravity is pulling this one inward. If there is no external force, the speed of this unit mass will increase. So in order to keep speed of this unit mass constant, we have to apply external force opposite to gravity. So this is direction of external force. And here we have gravity. But this gravity is not constant because gravity depends on distance. As the distance is decreasing, gravity is getting stronger. So the gravity is a variable force. So one point we need to understand is gravity is variable force. It is not constant. So the external force also has to be variable. Let's try to understand the work done by external agent. Work done by external agent has to be negative because the displacement is to the left and external force is acting to the right. So this is external force. So work done in this case by external agent is negative. Mean by external force, we can say work done by external agent, this one is negative. Simply we can define potential at point P by saying potential at point P is equal to work done by external agent from infinity to point P per unit mass. Now let's try to understand, is the potential at point P, is it positive or is it negative? Potential at point P has to be negative because the work done by external agent from infinity to point P is negative. So simply we can say gravitational potential is negative. And gravitational potential is always negative because gravitational potential at infinity is equal to 0. Based on these points, we can write down our answer. Before we write down our answer, if you're curious about VP, means the value of potential at point P, this is equal to capital G, capital M divided by the distance from center of planet. And this one is the mass of the planet, means the potential at point P due to this planet is equal to this. And this is negative because work done by external agent is negative. Now, if we have understanding of these points, we can write down our answer. In our answer, we have to write at least 3 points. So these are the 3 points you can write down in your answer. The first thing you can say, potential at infinity is equal to 0. As we have already discussed, potential at infinity is equal to 0. So let me write down here 5, potential at infinity is equal to 0. So this is 1 point. If you write down this, you'll get 1 point. And this is B mark. And the second, gravitational force is attractive. So work done by external agent is negative because gravitational force is attractive. So this is the second point you can mention. And the last point you can say test mass getting closer from infinity. Means when we move this test mass from infinity to point P, in this case the potential energy of unit mass is decreasing. So this can be the third point. If you write down these 3 points, you will get 3 marks. For part 2, it is given to us, one of the features of figure 2.2 is that phi is negative throughout. Means potential is always negative, starting from the surface of the planet to the surface of the moon. We need to describe 2 other features of figure 2.2. Other 2 features, if you look at the surface of the planet and the surface of the moon. So the one feature we can say that potential at surface of planet, we can say phi at planet is more negative than potential at surface of moon. So this can be over 1 point. For the second point, we can compare potential gradient at surface of planet to potential gradient at surface of moon. Means at this point. Here we have this point at surface of planet and this point is at surface of moon. So simply we can draw the tangent line and we can compare the gradients of tangent line. For the planet, this is how we can draw the tangent line, and for the moon we can draw our tangent line almost like this. So this is the tangent line. Now if we compare the gradient of these 2 lines, we can simply see that this gradient, this one is steeper, so this one is steeper. So simply we can say the potential gradient means d phi by dr at the surface of moon, this one is steeper, we can say is steeper than potential gradient at surface of planet. So this is for surface of planet. So this can be our second point. For this question, we have to mention only 2 features. If you write down these 2 points in your answer, you will get 2 marks. Let me show you the proper answer for this question with some extra points. This is how you can write down your final answer. In this case, we have mentioned first point, potential at surface of planet is smaller. Smaller means that potential at surface of planet is more negative than at surface of moon. So this is our first point. In the second point, you can say potential gradient at surface of planet is smaller than at surface of moon. So this is our second point. Third point, you can also write down magnitude of potential varies inversely with distance from center near the sphere. Means near the planets and near the moon, potential is inversely proportional to R. So this point you can also mention. And the fourth point, you can say point of maximum potential is near to the moon than planet. Point of maximum potential is where potential is less negative at this point, and this point is closer to the moon. You can also mention this one in your answer. But if you write down any 2 points out of these 4 points, you will get 2 marks. For the last part, we need to sketch g against distance, mean against x from surface of planet to surface of moon. First of all, let's try to understand how we can determine g from potential against distance graph. G is simply equal to negative of potential gradient. G is equal to negative of potential gradient. If we look at gradient of potential against distance graph, we can see that at the beginning this gradient is decreasing. So let me use different color. If you look at the gradient from this point, you will see the gradient is decreasing until this point, and at this point gradient is equal to 0, and after this point this gradient start to increase and this gradient is negative. So let me highlight some points. In this case, we can simply say that gradient from this point to this point, gradient is decreasing. So we can say gradient is decreasing and gradient is positive. So we can draw the line here. Now if you look at the second part, in this case gradient is increasing, so we can say gradient is increasing but gradient is negative. As g is equal to negative of potential gradient, so simply we can say in first region g has to be negative and g has to decrease, because g is equal to negative of potential gradient, means if gradient is positive g has to be negative. So same we can say about the second region. In the second region g is positive because gradient is negative, and g has to increase because gradient is increasing. Now we need to compare the gradient at this point, means at surface of planet, and we need to compare gradient at surface of moon. We have already discussed that potential gradient at surface of moon is greater than potential gradient at surface of planet. So simply we can say potential gradient at surface of the moon is greater than potential gradient at surface of planet. Surface of planet. As potential gradient is greater, it also means that magnitude of g at the surface of the moon is greater than magnitude of g at surface of planet. Now we have to use this knowledge to sketch the graph. So the first point we can see at this point g is equal to 0. So from here we can mark g is equal to 0. So this is about at this point. So g at this point has to be 0. And g at the surface of planet has to be negative. So it has to be negative. And g at the surface of the moon has to be positive. And now we can sketch the graph. So let me show you how you can sketch the graph. This is how you can sketch the graph. You can see here in this case g at the surface of the planet is negative, g at surface of moon is positive, and this one is greater, and g here this is equal to 0. That's all what we need to understand for this question, and if you write down these points you will get 3 marks.